All right, this video is about a transcritical, which means beyond the critical point, CO2 grocery refrigeration system. So a rack system is what this is often called. This video is made by Kevin Compass. Kevin is one of the smartest rack refrigeration technicians I've ever had the privilege of interacting with, and he gets a chance to work on a lot of CO2 systems. And so he was doing a commissioning on a new system and decided to just give us a quick rundown of that commissioning and the charging, adding CO2 to the system, as well as some features of the system. Now he jumps right into some advanced concepts. So this video will be valuable to those of you who maybe already have some experience with CO2 and you just want a little further knowledge of it, and also those of you who are completely new to it, this will give you some familiarity. But let's start by taking a look at this diagram from Emerson of a transcritical booster CO2 system. So a few things you need to know about CO2 is, first off, it has something called the triple point, which is the lower threshold on CO2 where it no longer exists in the liquid form. So we have to keep CO2 pressures above the triple point, which is why you often hear him talking about charging with liquid and making sure it doesn't change to a solid. So for example, CO2 at atmospheric pressure, we call that dry ice. It goes directly from dry ice and sublimates directly to a vapor. So we have to have it under high enough pressure in order to keep it from hitting that triple point at the bottom. And then whenever CO2 gets above about 87 degrees Fahrenheit, that's where it hits the transcritical point. Whenever we were using CO2 as a refrigerant, it gets very odd by our standards when you get above 87 degrees because it doesn't change into a liquid the way we're used to in condensing. It becomes what's called a transcritical fluid, which is really neither a liquid or a vapor. It's kind of its own thing, and it no longer obeys those sort of rules of condensing and boiling or saturation that we're used to. So when we're working in that transcritical zone, you'll hear Kevin talk about a gas cooler, and a gas cooler is essentially what we would normally call a condenser, and in fact does become a condenser when it's under 87 degrees outside, so it functions as a condenser. But then when it gets above 87, it's no longer condensing, it's now functioning as a gas cooler, and then we have to drop the pressure in order to get it to condense. So there's some interesting things about CO2. If you want a more advanced description of this, I've done a couple podcasts. I did one with Andre Pottenaud from Emerson a while back, and then also one with Rusty Walker from Hill Phoenix, and you can take classes from those organizations for a little bit more in-depth look at that. But just know that we have to treat CO2 a little differently. One, because it's very high pressure. So when we're on the very high pressure side, we have to use special tubing, either stainless steel or copper, that's specifically designed for those really high pressures. It actually has some steel in it. And then we have to kind of think of unique ways of designing the system in order to stay above that triple point on the lower level and to try to maximize what we can do before we hit transcritical. And so in this particular case, he's going to talk through the different controls and everything that goes into this transcritical booster system.
So this is our charging line up here. For some reason, they made us put this ridiculous relief on here. 3/8 charging line. We still got to put the tap on the end of it. Basically, what you do when you charge this system, you're going to hook a tank up downstairs. You're going to purge it out, and you're going to come up here. And then on this vessel, we're charging in the liquid. It's different. We don't charge in the suction. We're charging in the liquid into the vessel tank. So we have a tap on here and a ball valve. So you hook your line up to this 3/8 tap here. You open the tank up. You let it go in. You just keep feeding it in. You slowly open the tank till it's almost wide open. When the tank stops going, sight glass or pressure, whatever you got on here, that's when you know it's done. You can go ahead and turn the tank off. You just constantly got to watch your vessel pressure up here just to make sure you're not going to hit your relief and make sure both your compressors are going. You want about it has to be over the low liquid level indicator. I like to see between 1 and 2 balls floating. I mean, it's a little more CO2 than you need, but that way if it gets colder, you don't have any issues. You just want to be careful and make sure you don't pull the reliefs. So we're adding the CO2 in right now out of these siphon tube bottles that have a dip tube in them to allow liquid to come out like a refrigerant tank would. And we're just waiting for the sight glass to stop flashing. There's no really other way to do it besides having a pressure gauge on there. Not really worried about the hose blowing out of the sight glass. I mean, it's going into a vessel. It's 4 times as large as the tank, only running 500 pounds. We're charging right now. You see it's going pretty fast. It's about a minute to 2 minutes a tank usually. It's already kind of starting to die down a little bit. There's only about 50 pounds in one of these tanks. Pretty much empty. Disconnect it and on to the next one. So this is one of the cases that's using the CO2. So we have a suction transducer monitoring the suction temperature pressure. We have a suction transducer that we're using to measure the suction line. We have a coiled temp sensor for defrost termination.
Now, quickly, if you look at this diagram, you're going to notice down at the bottom right side of the diagram, you have the scroll compressors. And the scroll compressors are the compressors for the low temperature part of the system, so your freezers in this grocery application. But rather than having their own condensers like you would often have, instead these compressors, instead of discharging into a condenser, they discharge into the suction of the medium temp compressors. And so you see you have the scroll compressors on low temp and you have semi-hermetics and the medium temp, which is exactly what Kevin is describing here. And then those medium temp condensers, those are what discharge into the gas cooler / condenser, depending on the conditions. Then they go into that high pressure valve, the flash tank, bypass tank, and then your expansion valves back. So depending on your conditions, whether or not you are above or below 87 degrees, that's going to make a big difference in how those valves function and whether or not that heat rejector up on the roof that we would normally call a condenser is indeed a condenser, where it's condensing from vapor to liquid, or if it's just cooling the gas and then the condensing is happening after you have that pressure drop.
This is the oil system of the rack. We have a Westermeyer oil separator right here. See, it's got a large number of bolts on there. It is a coalescent oil separator, and it uses a filter that's inside of it to mist the oil out, and the oil drops down. Then there's this little sensor down here. When this sensor senses the oil level in the oil reservoir, it's going to open this solenoid valve right here, and it's going to pulse oil into this tank, this reservoir tank. We can maintain oil level to this sight glass, and it also has a level alarm right here. And then we're actually venting this tank off to our flash tank from this line right here. We're venting it off to our flash tank. This reservoir tank is always maintained at 500 pounds. It's 100 pounds over the medium temp scrolls, and it's 300 pounds over the low temp scrolls. So that way it can push oil into the compressor controls, the OMC controllers. So this line always has 500 pounds of oil on it. So we have plenty of oil pressure to go in here. It's a pretty good system. It's pretty trouble-proof until we get the transcritical mode. Pretty easy to work on. As long as the filter's good and separating oil, we should be good. So this is the back side of the rack where you can get to more service stuff. Here's our low temp system accumulators. We have one freezer for the entire store. It's a small chain store. We got our gauges for our low temp. We have our transducer, our pressure relief, our service tap for the low temp side. This is our low temp suction header. This is our medium temp discharge header. It's all copper over here. It's the stainless coming off the compressors goes into a copper header. This is all Mueller 130 bar copper. Then over here we have our heat reclaim valve. So we're using discharge gas from the compressors, from the high side compressors. So anywhere from 700 pounds to 1600 pounds. And we're setting this to one of our main store rooftop unit to reheat the air. We got two transducers on here. We got one right here and we got one right here. What we're doing is we're modulating this BLEMO valve to maintain no more than a 16-pound drop through the reclaim condenser, which we don't have, maybe a pound or two at the store. So not too much, so it's pretty much wide open or closed depending on what we're calling for reclaim, which the store is pretty much going to be in reheat most of the time anyway. Up here we have our high side gauge. So this rack pretty much has gauges and transducers all over it. So you can't use a gauge unless you have a hydraulic gauge on this side. This is our high side vapor. So right now we're running about 1,000 pounds on the discharge. Our equalization for the heat reclaim. We got our main high side relief, our 120 bar relief, 1740. So the main discharge release is 1740. Then up here we got our flash tank reliefs. So we got a 650 and an 800. So our 600 and 800. One's a working relief, one's a service relief. Then right here we have our main block for our flash tank. We got our pressure gauge. We got our EMS transducer, flash gas bypass, and high pressure regulator transducer, which we'll go over that in a second. Our oil line bypass bleed out on here. So that's what we're using for that. Then we have our liquid, our high side drop leg transducer, EMS drop leg transducer and a service port. So over here, we have our gas cooler. We got our drop leg coming out of the gas cooler, comes down. It comes back up to here.
One word you're going to hear Kevin use here is drop leg. And drop leg in refrigeration is the line in between the condensers and the receiver. So in between the condensers and the receiver is the drop leg. So generally the line that comes down from the condensers, that's what they call the drop leg. Generally tend to call that in air conditioning the liquid line. But in grocery refrigeration, the line that leaves the receiver is what they would call the liquid line most often. And the line between the condensers and the receiver is what they would traditionally call the drop leg. You'll notice here that you have 400 PSI suction. And so that's what you're going to see on CO2. You have much higher head pressure and you have much higher suction pressure than what we're normally used to. But again, it all comes down to what is the saturation temperature of that refrigerant. Another thing you see a lot with CO2 is you'll see the pressure measured in bar. And bar is sort of a European pressure standard that's used quite often. And a bar is 1 atmosphere or very close to 1 atmosphere. It's 14.5 PSI or approximately 14.5 PSI. And so as you know, our atmospheric pressure is, 14.7 PSIA at sea level. And that's where they get that 14.5 from. So 1 bar equals 1 atmosphere of pressure. So 2 bar would be double that, so on and so forth. The way I like to think of a flash tank is sort of like how in a metering device, a typical metering device, we have high pressure liquid and then we drop the pressure and then it starts to evaporate. In this case, we have transcritical gas, a transcritical, it's not, I can't really say vapor because it's not vapor, but you have this transcritical gas, and in order to get it to condense, we have to drop the pressure. And so we do that in that flash tank. We drop the pressure and now it actually can condense and become a liquid before we feed it into those metering devices. Regardless of whether or not that piece on the roof that rejects heat is a gas cooler or a condenser, either way, its job is to reject heat to that atmospheric air. It just has to do it a little bit differently depending on those outdoor ambient conditions. And of course, it does it more efficiently when the temperatures are below 87 than when they're above 87.
We're going to hit our high pressure regulating valve. So we have this valve right here, this Danfoss valve. It's a high pressure regulating valve. And we have, right here is our flash gas bypass. Comes off the top of the receiver. What we're doing with these 2 valves, they're accomplishing 2 things. They're working together. You get your high pressure regulating valve is constantly going to be holding back gas in the gas cooler, and your flash tank bypass valve is going to constantly be venting off the top of the receiver / vessel into the medium temp suction header in order to condense the CO2 back down. Because over an 87 degree temperature, CO2 no longer is a liquid, a vapor, or a gas. It's transcritical. It's an unstable fluid. So what we have to do is we have to falsely turn it back into a liquid. So what we do is we hold back a little bit of pressure. We open the flash gas bypass to reduce the tank pressure. We get it down to 500 pounds. And the tank starts to, it's about a 30 degree evaporator or 30 degree condensing temperature. The tank starts to drop pressure and temperature at the same time, and we end up with a liquid again. So this valve is constantly shutting and opening. They're working in unison together to keep this tank at a certain pressure. This valve is constantly looking at the discharge pressure, drop leg pressure, and the tank pressure to make sure it doesn't high head the rack or starve a tank. And then this valve is constantly looking at a tank pressure to try to bleed out the tank and to keep it at a certain pressure in the tank. That's how this is working. We're basically recondensing CO2. When the ambient's low enough, we're barely going to be opening this flash tank bypass valve, and then this is going to start acting somewhat like a holdback valve to keep the pressure up in the gas. This is our gas cooler. So we got a 4-fan ECM gas cooler. Below 87 degrees, it's a condenser. Above 87 degree condensing, it's a gas cooler. It's only cooling gas. So we got our ECM fan motors. They're barely spinning up here. It's only like 50 degrees outside today. That is how the flash tank bypass works. This is our suction shell dryers. We only have suction shell dryers in here. They got liquid cores in them each side. Each group has a suction shell dryer on it. Then up here we have our hot gas injection. So what we're doing is injecting hot gas into the medium temp side. So if the superheat gets too low from this flash tank bypass or the superheat coming back, it's going to start injecting hot gas into the suction group to maintain the superheat. And then down here we have our liquid injection valve. It's doing the same thing. If the superheat gets too high from the low temp compressors discharging there. It's gonna de-superheat the medium temp side to keep the compressors from overheating. So this is our main electrical panel in here. We're using CPC for our controls. We have our digital compressor controller that's using pulse width modulation to modulate the solenoid on here. We got our normal compressor, just straight up normal contactor. And over here, this is the EKC valve driver that's driving the CO2. Flash tank bypass valve, and it's communicating with the high pressure valve. So it's constantly monitoring and changing the valve driver from here. This is our filter. It's constantly opening and closing that valve to maintain everything in here. These boards are monitoring all the dry contacts for all the level switches and all of our temp sensors and our analog outputs for all of our compressors. This is our main controller. This is the front end we're using. So you can see you got your low temp suction group on there, all your case temperatures, your gas cooler, sensors. So we got our medium temp suction on here with our variable capacity compressor going up and down. Discharges, we're running 866 pounds right now. We're running 400 pounds of suction pressure. And then in this door, we have all pulse valves. So we're using Dixel XM 679s. These valves are pulsing up and down. We have our evaporator pressure, coil outlet temperature, your valve percentage that it's pulsing 42%, your superheat's 12 degrees, its set point is 10. So these are going to try to maintain temp and superheat. 35 degree box temp, it's trying to maintain 34, so it's a degree off set point, so that's why it's opening. These are going to maintain temperature and superheat second. So as long as the superheat isn't low, it's going to keep opening the valve till it hits its predetermined spot where I had limited the valve opening. We got our meat cases here. Each case has its own controller, own temp sensor, own valve. I'll show you downstairs a little bit. We have a liquid line dryer in here. We have a pulse valve. This valve is just pulsing a solenoid on and off, on and off, on and off to maintain superheat that is calculated from the controller from the suction pressure or the temperature and the temperature sensor. It's pulsing the superheat that way. And it's pulsing the valve open, allowing liquid to come in and feed the coil. So that's how it's doing it. It's superheat control and defrost. So when it shuts off, it just stops all flow. This is the transcritical CO2 rack we just started up. You got 2 low temp compressors, 410A scrolls, and you got 2 medium temp compressors. So this rack is transcritical, so it's actually compressing CO2. We got the CO2 scrolls over here. You have 1 digital compressor, 1 normal compressor. They're using Emerson OMC oil controls. Discharge header back here for the low temp flows up and into the medium temp suction header. So what we're actually doing, this is a 2-stage rack. We're taking the discharge gas of the scroll compressors and we're discharging into the medium temp suction group to reduce the compression ratio, or else we would be going from 200 pounds to 1,200 pounds to 1,600 pounds, depending on the outdoor ambient. That would be a huge compression ratio and a huge efficiency loss. So we are instead going into the medium temp compressors. Why they're so much larger, they have so much more of a load on it. So our medium temp compressors, we have 1 standard compressor, and the number 1 is a variable speed drive compressor running off of VFD over here on the other side. So we have a Danfoss VFD up here controlling our compressor based off the signal. We have our oil fill here. When the ball gets down, it fills up oil from the reservoir. Go from the oil system next.
All right, big thanks to Kevin for taking the time to do this. It's always time-consuming to pause and pull out your phone and take some videos, and I appreciate it anytime someone does that for the benefit of helping train the trades. I think the old school thinking of, hiding information so that new people don't learn, those days are over. It's all about sharing, so that way we can get more people in the trade, so that way we all don't have to work such crazy hours. So thank you, Kevin, for doing that. I really appreciate it. So hopefully you learned something in watching this. If you want to learn more about this, you can go to companies such as Hill Phoenix, Kaiser Warren, Emerson, all great resources for CO2 training. And like I mentioned before, we have a couple great podcasts in the HVAC School archives, one with Andre Patinaud from Emerson and one with Rusty Walker from Hill Phoenix. Those podcasts help describe this in further detail. But hey, thanks for watching. We'll catch you on the next one.